Hi, my name is Chiara Bruzzi, and I'll be presenting the evolution of magnetization plateaus in frustrated systems. I want to recognize my mentors and my sponsors for giving me this opportunity. A little bit of an outline of this talk. We're going to be looking at the introduction and specifically the quantum mechanics behind this project, the density matrix renormalization group, which is the numerical method used to run these simulations, and finally, some research goals and results. So what's the objective of this project? The objective is to investigate the characteristics of magnetization plateaus in the anisotropic Heisenberg model on a Kagome strip chain at 0 Kelvin. Anisotropic means that the properties vary depending on the direction. Heisenberg model is a mathematical model used to describe the behavior of magnetic systems, specifically those between spins or atoms. And it's represented by the Hamiltonian here on the left. And the Kagome strip chain is this lattice structure on the bottom, and it's simply just a geometric arrangement of atoms. The Kagome strip chain is a frustrated lattice. So as you can see here on the bottom right, that means that the spins do not cancel each other out. And this project is based on the finding of the nature, origin, and stability of these frustrated systems. It attempts to look at new magnetic behaviors and materials, as well as expanding the fundamental knowledge and quantum understanding and computing of these systems. The motivation behind this project is mainly motivated by previous studies of magnetization plateaus, and they want to better understand the anisotropic effects and inhomogeneity of frustrated systems. The magnetization plateaus, you can see here from this bottom right figure, is when the magnetization does not change with increasing magnetic field strength. So what are these magnetically frustrated systems that we're talking about? To explain these, we're going to be looking at the comparison between frustrated and non-frustrated systems. So non-frustrated systems, you can think of iron, BCC, body-centered cubic, and the magnetization curve for this material would be an exponential curve until it reaches a plateau at the saturation. Saturation magnetization is the limit where, as you increase the magnetic field strength after that, the magnetization does not change. This happens for systems where the spins cancel each other out, as you can see by the square here on the top right. For frustrated systems, as you can see by this triangle, the spins do not cancel each other out. So as you decrease the magnetization from its saturation, you encounter these plateaus. What is the Kagome strip chain? Let's really get into that because that's the model that we're going to be looking at. And that's an example of a frustrated system because these frustrated systems require amorphous arrangements that are a little less common. So the Kagome strip chain is, you can see here, this is one unit cell and this is another unit cell. So it's a upside down triangle and regular side triangle, put one on top of each other, and there's 5 different sites, so there's a spin at each of these sites, and they're attached by this hexagonal shape. So the chain is many of these Kagome structures attached by this hexagonal shape. And this lattice structure is often found in certain transitional metal compounds, particularly those with 3D transition metal ions. The unit cell size is important because you will see different magnetization plateaus and characteristics depending on the unit cell size. So what we found was that we're going to be using 2 unit cells because that gives a practical approximate of the magnetic structure. L is equal to 6 would have perhaps been a better unit cell size that would have given a more accurate description of the ground state as it captures all of the different possible magnetic structures of 1, 2, and 3. However, if we were to run all of the results at L is equal to 6, then it would take a very long time to run these simulations. We also tested the results for L is equal to 1 and L is equal to 3, but we found that L is equal to 2 was the best. The Kagome strip chain uses the Hamiltonian that we previously introduced, but the class parameters for the code for these simulations, since we're running these at 0 Kelvin, so it can't be done in an actual laboratory, those actually come from the Hamiltonian. So you have delta Z, which is the anisotropy of the Heisenberg interaction, and that comes from here. DZ is the single ion anisotropy, so that's here. JH, JU, and JD are between the bonds, as you can see from before. So JH is the horizontal bonds, JU is the upper two green bonds, and JD is the bottom two red bonds. And then S is the single ion anisotropy. So S is all of these S's that you can see. These are just in different directions. L is the unit cell size, which we talked about, and BC are the boundary conditions, which are kept at infinite, which means infinitely long chain. So there's a lot of these Kagome structures, but we are looking specifically in periods of 2. The density matrix renormalization group. So this is the DMRG, which is a non-perturbation numerical method that offers high accuracy in approximating the ground state wave function for large systems in low dimensions. And I've included here the formula for the wave function that it approximates using the matrix product state. So this is just showing how you multiply matrices and then add them together. So let's get into a little bit of the results. First, we wanted to look at the plateaus at a magnetization of 0.2 and 0.6 because those were the ones that in literature were previously found and confirmed. And we looked at a region for H. H is the magnetic field strength of 0 to 3. And we did find those plateaus at 0.2 and 0.6. But next, we wanted to look at new plateaus because that's the whole point, is to expand the knowledge of these magnetic behavior of the frustrated systems. We also were looking to confirm the existence of the plateaus that studies had previously looked at, but weren't able to confirm. So those were plateaus at 0 and 0.4. To do so, we looked at a more localized magnetic field strength region. And so for the magnetic field between 0 to 0.015, we were able to find that perhaps there is this possible plateau at a magnetization near 0. And we were able to see that this might be a plateau because between 0 to 0.015, the magnetization values vary by an amount that's within the error limit. So in theory, these could actually all be the same value. It's just that the error limit does not allow for them to be exactly the same. For the 0.4 plateau, what we found was that between 1.4 and 1.6, the magnetization was exactly 0.4. So even though the error limit was 10 to negative 11, it was exactly 0.4, which also showed that this is perhaps a plateau. But we really wanted to be sure, so we wanted to run a little bit of a more test on this to confirm their existence. So we looked at the spin correlation, which is the relationship between two spins. And what this spin correlation shows is that if there is a periodic arrangement, then it indicates a fixed state, if you will. And if there's this fixed state of the spins, then there's an energy gap, because in order for these spins to change their arrangement, then they need to reach a threshold magnetic field strength, which means that for a certain region of the magnetic field, they're going to be the same and therefore form this plateau. So we looked at the spin correlation, and what we found was that for both the magnetization of 0 and 0.4, there is in fact this periodic arrangement. So these diagrams are showing this is one unit cell, this is the second unit cell, and this is the hexagonal shape that connects them. And the black solid line denotes a negative spin correlation. The thickness denotes the magnitude of the spin correlation. And the blue circles are the positive spins, and the red circles are the negative spins. So the next part of the project was to vary the delta Z parameter, and I just want to show again that this is the delta that's part of the SZ parameter. And we are just doing that to see how that might change the plateaus. And we actually found that it does change the plateaus because as you decrease delta, the 0.6 plateau and the 0.2 plateau are no longer there in this region. Another interesting result was that as you decrease delta, it seems that the magnetization curve does not reach the saturation of 1, which is perhaps an unexpected result that we're looking to investigate further. Next steps would be to vary the JD parameter, and we're going to be doing that for L is equal to 6 unit cells. Since this is between sites, we want a very accurate unit cell size. And then we're also going to be adding a delta X component, that you can see here. So there'll be a delta component, and we'll be looking to vary that and see how that further varies the results. Thank you, and I hope you have a great rest of your day.